Hi, everyone. Welcome to your lecture on understanding biomechanics, or a general introduction to biomechanics for physical educators. So let's go ahead and jump in. So if you're sitting near someone, or even if you're by yourself, pause the video and just kind of think about what biomechanics is. Maybe have to look that up, and then how that plays a role in physical education, teaching physical education, and working in the health-related field. Now that you've done that, let's talk a little bit about that. So, for physical educators, we do want to talk about kind of why we want to talk about biomechanics for a little while in this course and over the next few weeks. And so, part of that reason is kind of um, the big organization related to physical educators, health and physical educators, is Shape America, and so they recommend that all physical education students. Have a knowledge about biomechanics, and the having a knowledge of basic and applied biomechanics is helpful to looking at human beings, especially when it comes to movement. So uh, when they talk about the course, a course in biomechanics, they think it should provide students with a basic knowledge of biomechanical foundations of human movement, the skills necessary to kind of analyze human movement, and the ability to determine and provide interventions that are likely to improve movement. So, if we see movement and we see that it's not being the most effective, how can we change that or help a student make those corrections so they can be more efficient or prevent injury or become better at their movement skills? And so they want to make sure that students can observe and describe movement patterns accurately, that you can determine the basic anatomical and mechanical factors associated with performance and movement, evaluate someone's performance technique with a reference task. So, are they kind of doing it similar as what we expect? And then, can you see the things that may limit someone's performance and then figure out how you can correct those things in the appropriate order that will help them improve that? And so that's kind of the goal as we move forward. So we have to kind of understand what biomechanics is. And so biomechanics is the physics or the mechanics of motion exhibited or produced by a biological system. So there are biomechanists that look at different animals and horses and things like that. We will focus on the human subject, of course, and it's a very highly integrated field. It takes a lot of interdisciplinary kind of knowledge, like a lot of things do in the healthcare world. You have to know a lot about a little bit about a lot of things, and then some things you have to know a whole lot about in order to be able to look at them appropriately. And so they're looking at forces and what's acting on those forces within the body, outside of the body, and the forces that our body produces. And so there's an image of some of the things that someone may evaluate with different angles and forces coming from the feet, coming up to the body, with what looks to be a golf swing in this picture. So, in addition to this, we also see that biomechanists kind of maybe where it was developed a little bit more intentionally, where there was more intentionality with biomechanics, was through some of our Olympic committees. They started to encourage the development of biomechanics into a deeper realm in order to improve elite athletes' performance. And so, a lot of times, you'll see things when it comes to human performance starts at the top level, and then we figure out, well, this can be beneficial at every level, and then even at the limited level. And so, if you ever get the chance to visit an Olympic training center, they have the most state of the art technology and sciences used to help analyze and test for performance and then change those for athletes to make them improve, even if it's just by a tenth of a percent. That could be the difference between medaling in the Olympics and not. So the reason that we continue to study biomechanics is to better understand the human body and the various internal and external forces that affect our movement. It gives us a scientific foundation to improve performance, improve sport techniques, even equipment and safety are improved with biomechanics. And so it also helps us to design and conduct programs to enhance an individual's movement skills. So this could be at the elite level, but also think physical therapy for someone who's had a surgery or had an injury is going to use a lot of these biomechanical principles, especially at the basic level. And those were what were to develop those, along with physiologists and other things as well. So there are several areas of specialization, and these can get very specific, but the broad areas of specialization are developmental biomechanics, so studying the movement patterns as we move across the lifespan and with varying disabilities. So as you're moving from child to adolescent, how do those biomechanics change? You have biomechanics of exercise. So, how do we maximize the benefits of exercise and reduce injury? Rehabilitation mechanics, so study of improving movement patterns with injuries or even disabilities. And then you have equipment design, so being able to change equipment to increase performance or prevent injuries or various things like that. So, all about equipment. So, with that, the biological aspect is underlying human movement, so that's always something to be looking at. Is there is the biological aspect, so you do have to take that into account. And so when you're looking at mechanics specifically, there's two different types of ways that a biomechanist can look at the mechanics or that physics of movement. There is the static, so the study of factors relating to non-moving systems, so steady motion, things like standing in one place or various things like that and tend to be what you see a little bit more of, but isn't any more important. It's just there's more factors that go into it. Is dynamic mechanics, and so this is a study of mechanical factors that relate to a system in motion. So static is staying still, dynamic is moving, and with dynamics, there's two different subsets of that, which is kinematics and kinetics. And so what you see with some of the research questions that can develop through some of these major areas of um, biomechanist research are things like, do running motions change as children develop? So the way they run, those mechanics change. So um, the way we move our legs and our arms. How do forces summate or sum up to produce maximal power in a tennis serve? So how do we get the most power out of a tennis serve to serve the quickest and still be accurate? How can athletic shoes be designed to reduce injuries on artificial turf? Or even what is the best body position for swimming the butterfly stroke? What's the best way to do that? And so we do want to talk a little bit about the difference between kinematics and kinetics. So we mentioned that before. So kinematics is the study of the concepts that describe motion. So how far, how fast is it speeding up? Is it slowing down, etc. So really the concepts of describing motion. Kinetics, on the other hand, is the study of what actually is causing that motion. So force is usually the major thing looked at with kinetics, but there are other things as well. And so it's usually how is the force applied? How long is it applied? What direction is the force applied? What is maybe resisting that force in order for you to see what's going on and make adjustments or recommendations? So, in biomechanics, there are a lot of terms that are really important and used a lot. You typically see these terms used very heavily in physics as well, because again, they're very related. We just kind of apply ours to biological movement instead of planets and things like that. So, you have velocity, which is the speed and direction of a body, or so think of a body running, so the speed and direction it's going. Acceleration is change in that velocity again involving a speed or a direction. You then have angular velocity. So just like velocity, it's talking kind of that speed of direction, but with angular, we're talking usually about an angle. So think about a circle. If you draw a circle, we call that 360 degrees. What angle what angle is it being rotated in a given unit of time? So how many degrees are you moving? So think about your shoulder. If you move it up and down, what angle? How much is that angle changing over a given amount of time? So maybe 1 second. And then angular acceleration is applying the term acceleration to this angular thing. So uh, the change of angular velocity over unit time. So how quickly are we speeding up or slowing down that angular velocity? So another important thing is to look at um, we are always looking at a body, and so in human biomechanics, we're looking at the human, and so it's important for us to know anatomical positions. And when someone references the right side or the left side, or is trying to refer to specific areas, they use this anatomical position to kind of reference the body. Even if someone is moving uh, in a different pattern, we can always find the exact location based on thinking about this anatomical position. And so it's kind of a reference spot for the body. So the way anatomical position works is you can see the picture, that is anatomical position. So standing tall, all joints fully extended, feet are parallel to each other and pointing straight out to the body, or pointing straight ahead of kind of where the eyes are looking. Palms are always facing up, so the thumbs are kind of on the outside of the body and your fingers are together. And so this is anatomical position. So the reason this is important is when we start to talk about things, we can reference them and always make sure we're looking at things in the same way, and people can kind of replicate what's going on. And part of this is in biomechanics and in any kind of health related area, we use these directional terms that help us describe different things in the human body. So medical professionals use these a great deal, but so do health professionals and exercise physiologists and biomechanists especially. And so it's a way to refer to the body and different things. So if we're trying to reference one point, or if we find a major landmark on the body that everyone can recognize, like the nose, and we want to get you somewhere else, how do we get you there? And it's used through these terms listed on the screen. So you have things, again, looking at that anatomical position, you have a term called superior. And so this is upper or above one another. So the head is superior to the feet, meaning it's above the feet. Inferior is the opposite. So most of these terms are kind of combined into terms that are antagonist or exact opposite of each other. So inferior is lower or below. So the feet are inferior to the head. Okay, and so you can kind of see that. And then we have other terms. So we've got medial and lateral. So medial is talking about the midline of the body. So think about your nose is in the middle of your body. And so we can talk about things being medial or lateral. So your arms or your arms are lateral to your stomach. So that means they're more towards the outside of your body than your stomach is. Your nose is more medial than your ears. So your nose is more towards the center line of the body than your ears are. Um, you then have proximal and distal. And so this is talking about proximal is things that are closer to kind of the center of the body. So kind of think your core, kind of your chest area. Distal is further away from that. So your fingers are distal to your elbow, and your shoulder is more proximal than your elbow. And so you can kind of see that comparison. You do have right and left, and so when you're talking about right and left, if you're looking at someone in an anatomical position, it is their right and their left when you see those terms. And so then you have anterior and posterior. So this is if you're looking at someone from the side. Anterior is more towards the front, towards the face side. Posterior is more towards the back or the butt side. You also have planes of system in motion. So you have frontal, sagittal, and transverse planes. And so those are represented here in the picture. And so frontal passes directly through the midline of the body and kind of cuts the body from an anterior and a posterior side. So you can, a frontal plane is going to cut it from anterior and posterior, so a front and a back. A sagittal plane is going to make a vertical plane that divides the body into a left and a right. Okay. And then a transverse plane is a horizontal plane that divides the body into a superior and inferior half. And so those are seen there. And so there are different ways to look at the body and reference motions. And so just kind of keep that in mind as you go through looking at some of this and we talk this semester. So here's a video that explains the planes of motion. So please download the lecture video and watch that. I won't play that right here, right now. But you guys can log in and watch that. You can also simply look at ACE planes of motion video, and that will get you there as well. So other biomechanical terms, we have mass, which is the amount of matter possessed by an object. So mass is not dependent on gravity. Where your weight is dependent on gravity, you would weigh more on a different planet or weigh less on the moon, but your mass stays the same. You have force, which is an action that changes or tends to change the motion of an object. So you have the guys playing tug of war. And then pressure is the ratio of force over a given area. So your feet provide pressure over a certain area, and so we can look at that pressure on your feet. If you have bigger feet, or if you make a wider surface area, so if somehow we were to give you bigger feet, there would be less pressure over that given surface area because your weight has stayed the same. Or for some people, if you reduce their weight, you can reduce how much force is being applied over their feet that are the same size, and reduce the pressure and possibly reduce pain. Other biomechanical terms, we've got gravity, which is the natural force that pulls us to the center of the earth. And so this gives us a center of gravity. So where's that center point that's pulling us down? We also have friction, the force that occurs when a surface comes in contact and the result of sliding over one another. So friction is when two surfaces come in contact and they kind of slide over each other. What is that force that is keeping them or helping them stay kind of in stay together and not move across one another? We have work. Work is simply a force that is applied to a body through a distance and a direction of that force. So if I'm pushing a box over, how much work is it taking to move that box, let's say 10 feet across the ground by pushing it? Power is the amount of work accomplished in a unit of time. So it's very related to work. It's work over time. So you kind of have that that you're looking at. So work and power are very related, but power adds this unit of time to it that it accomplishes. And so the example for this is think about running or walking up a flight of stairs, the same exact flight of stairs. You're going to walk up at once and run up at once. That's going to require the exact same amount of work. You moved your body up those stairs the same distance. That required the same amount of work. Same force, same distance, same work. Running does it faster. So what does this tell you about power? So think about that. What does that tell you about power? If it takes the same amount of work, but running happens faster, what happens to the power when you run up the stairs? So power needed to increase because you did the work faster over a shorter period of time, or you did the work faster and did it in a shorter period of time. Energy, so that's the capacity for the body to perform work. You have kinetic and potential energy. So kinetic energy is energy that's performing work. There is motion occurring. Potential energy is stored energy, so it can do something, but it is not currently. And so you've got the picture there. And then you have torque. And torque is twisting or turning or rotary forces that relate to producing angular acceleration and velocity. So again, going back to those angles, so going a little bit more to the trig side of this. So one of the big things with mechanical principles that we look at is stability. Stability is really important when we look at all of these things. So lowering the center of your gravity to the base of support gives you greater stability. So most people know this. If they really need to be stable, they get closer to the ground. Nearing the center of gravity to the center of the base of support is more stable. So think about the center of your state. If the center of gravity is not directly over the base of support, you're less stable. So when you reach out and like leaning over to grab something, you're less stable than if you're able to keep your center of gravity directly over your feet. And stability can be increased by widening that base of support because you can keep the center of gravity within that base of support a little bit more easily. So you have more room to move before you become unstable. Another thing is with our motion, we do have two types of motion. We have linear motion, so movement in a straight line from one point to another. And we have rotary motion, which is movement of the body around the center of a rotational axis. So you've got your 100-meter sprint, linear motion, and then your rotary motion, your shot putter who's about to spin around and throw that. There is a center point, a rotational axis for them. And you can get more complicated and start trying to combine the two. We keep it simple for now. We also have leverage. So a lever is a mechanical device used to produce a turning motion around a fixed point called an axis. Okay, so a lever is something that we start to it's a mechanical device to usually assist us make things easier to produce a turning motion around a fixed point. So there are different components to a lever, and we'll get to some specific examples, but there are three portions to this. There's a fulcrum, so that's the center of axis where rotation happens. So kind of where are we centered, where are we connected to something that is going to allow us to move around that particular axis is a fulcrum. So it kind of keeps us grounded and we move around that for our axis of rotation. There's a force arm, so this is some distance from the fulcrum to the point of application. So a force arm is where are we applying our force to make work happen. So what's causing our force to happen? and where is that in relationship to our fulcrum. And then our resistance arm is the distance from the fulcrum to the weight or the resistance which force is being acted on. So what is trying to be moved. So the resistance arm is kind of the weight or the resistance that we see and its relationship to the fulcrum. So when it comes to levers, there are three different types of levers. There are first, second, and third class levers. So first class lever, think about a seesaw. With a seesaw, there's a fulcrum between the weight and the force. So with that, the fulcrum's dead in the middle. So it's kind of what the seesaw sits on. On one side, if you put some weight on it, that would be so your buddy sits down on the ground. He's sitting on the ground. He would be the resistance arm, and then you want to try to lift him off the ground. You would be on the other side of the fulcrum, and you would be the force arm trying to push down on the seesaw to lift your partner up. So this is a first class lever. Resistance arm on one side, force arm on the other, and the fulcrum is in between the two. And depending on where that fulcrum is, can make it easier or harder to move the weight. Second class lever is, think about like a wheelbarrow. So a wheelbarrow, what you have is the wheel itself would be the fulcrum. The wheel itself is the fulcrum. The weight comes next. So that's where you put kind of the dirt, the mulch, trash, whatever you're putting in the wheelbarrow, concrete. The weight is next. So it goes fulcrum, weight, and then the force arm comes last. And so you're picking up at the end of the wheelbarrow. The weight is between you and the fulcrum. And then finally, we have third class levers. Third class levers are probably the most common we see as it comes to kind of muscle structure. And this is where the force is between the fulcrum and the weight. So kind of think about almost reversing the wheelbarrow. So the fulcrum comes first, and then the force is applied in the middle, and then the weight is on the outside. And so a lot of times if you see a crane that is trying to stand up, let's say like a telephone pole, this is how that particular lever works. The base of the telephone pole is sitting against the ground, almost in the hole. The crane picks up the pole somewhere across the pole, like maybe in the middle, and then most of the weight is on the outside of the pole. And so they're picking up from the center, trying to pick the weight up so that the pole stands upright. Our muscles work the same way. If you look at your forearm, your biceps are what brings your forearm or your hand towards your face. So if you extend your arm outward, your bicep, when you contract it, pulls your hand to your face. Well, your fulcrum is your elbow. Your biceps are attached just slightly more proximal than your elbow. So we're using those terms. So right there at your elbow. And if you have anything in your hand like a cup, that would be the resistance arm. And so it's further away from the fulcrum than the force is. And so you have fulcrum, force, and then you have your resistance arm. And so those are your different levers. And so when it comes to those, there are some other things we want to look at with, again, those mechanical principles. So we had levers, so forces as well. There are different things to look at with force. So there's the production of force, so produced by an action of the muscles. The stronger the muscle, the more force you can produce. So the production of force. You have the application of the force. So how is the force applied to an object? Where is it most effective? How is it most effective when it is applied? Are you going against it? Are you pushing with that object? So you're applying a force in the same direction it's already moving. And then you have the absorption of force, which is the impact of a force against you. And that should be gradually reduced given with the force and spread over a larger surface area. And so those are some different mechanical principles as it relates to force. That kind of covers our lecture. If you guys have any questions, please shoot me an email. Hope you guys were able to learn some more from that, and we will talk to you guys in the next lecture.